This is the presentation on optimal path planning using RRT star-based approaches, a survey, and future directions. Giving a brief background, optimal path planning finds the path between the start and goal position that is collision-free, shortest, and with smooth route. Once the optimal path is obtained, it is used by various robotics applications such as autonomous car, agricultural robot, space and planet exploration missions. RRT star has gained immense popularity due to its applicability for high-dimensional problems. A significant body of research has addressed the problem of optimal path planning, but there is no any updated survey available on RRT star-based approaches. So, the following paper presents a comprehensive review of RRT star-based approaches. RRT star stands out among other planning algorithms because initial planning techniques were unable to deal with dynamic and complex problems. Computational complexity of these initial planners limits their application to low-dimensional problems. Grid-based algorithms such as Dijkstra, Wavefront, A-star, and D-star were unsuitable for high-dimensional problems due to their expensive computational requirements. Sampling-based algorithms have low computational cost applicable to high-dimensional problems with better success rate. PRM-based methods are widely used in highly structured environments and for holonomic robots. RRT and RRT star-based approaches are well suited for non-holonomic constraints and for dynamic environments as well. The survey results are as follow. RRT stars shown in first column is vanilla algorithm, but it has various limitations like slow convergence, suboptimal path, and large memory requirements. Anytime RRT star improved trajectory and computational efficiency in simulation and in real-time implementation, an optimal variant of RRT star and RRT connect called bidirectional RRT star or BRRT showed empirical results indicating fast convergence and path refinement using sample rejection, though this procedure selects only promising nodes but also affects space exploration. Moreover, attempt to connect both trees in each iteration incurred computational overhead. RRT star was suffering from high memory consumption due to large expansion of the search space. RRT star fixed nodes is a memory efficient version of RRT star. It allows limited number of nodes in tree. When the tree is expanded to a preset fixed number of nodes, then new node can only be inserted by deleting the old node. An offline variant of RRT star called RRT star Smart to address the issue of slow convergence was implemented. RRT star Smart introduced two major features called intelligent sampling and path optimization. Initial path finding procedure is similar to RRT star. However, once a path is found, it is optimized based on triangular inequality principle to remove redundant nodes. Optimization tasks generate bigger nodes to further improve path cost. However, intelligent sampling has a trade-off between rate of convergence and rate of exploration. Another bidirectional RRT star was presented for optimal path planning, also called optimal B-RRT star. It improved convergence rate using a number of heuristic techniques. However, use of multiple heuristics also increased computational overload. Moreover, these biased heuristics interfered with the algorithm characteristics and limited its application. RRT-Sharp was developed to address the issue of slow convergence. It used two processes during each iteration, namely exploration and exploitation. Exploration performs the extension process, whereas exploitation uses a global replanning procedure to keep track of promising nodes. Promising nodes are the ones which are good candidates to contribute in the final path with lowest cost. Hence, it makes fast convergence by expanding the promising nodes towards the goal region and exploiting available node information to the highest degree at each iteration. In recent years, many RRT star-based planners were focused to solve the optimal path planning problem for car-like robots dealing with non-holonomic constraints. To overcome the above limitations, adapted RRT star was implemented. The proposed approach found asymptotically optimal trajectory for a car-like robot with a 5D state space and aerial vehicle with a 10D state space. Spline-based RRT star for non-holonomic path planning of fixed-wing UAV in 3D environment was developed. It expands the tree by using a cubic Bezier spline curve. This enabled RRT Star to produce smooth and cost-optimal paths in 3D simulations using a model of UAV. Inform RRT Star was presented for optimal path planning in narrow passages. Once an initial path is found, it further explores configuration space with a limited elliptical area. As area of ellipse decreases, it also improves the rate of convergence and path quality. Intelligent bidirectional RRT star was proposed for complex cluttered environment. It uses an intelligent sample insertion heuristic technique. Results of IBRRT star showed fast convergence towards optimal path using less memory resources in comparison with RRT star. A kinodynamic variant of RRT star called dual tree RRT manages two trees called state tree and workspace tree. At first, workspace tree explores targeted environment without considering any physical constraints. Then, state tree generates trajectories from workspace tree nodes using kinematic and dynamic constraints. The proposed approach showed better computation time. However, the algorithm is only useful for known or partially known environment. An offline cost-aware RRT star was developed for energy-efficient optimal path planning in high-dimensional space for humanoid robot. The approach used two trees to address the dense sampling issue in RRT star. First tree is a standard RRT star tree to determine nearest node for newly sampled point, whereas second tree contains first tree to extend additional long branches. Homotopy-aware RRT star is inspired with the idea of homotopy, that is, to plan the path from one topological space to another by human intervention. This approach addresses the planning problems of human-robot team interactions such as in search and rescue operation. Recently, RABIT star was proposed to address the problem of planning in high dimensions. It focuses homotopy class which are difficult to sample, for example, narrow passages. This was extended by an informed global technique called PIT star to improve an initial suboptimal path towards a local optimum. Thus, this approach preserved global optimal convergence. The following table shows various attributes of RRT star based approaches. RRT star can be used for holonomic and non-holonomic constraints. The term non-holonomic refers to the differential constraints that are not completely integrable, such as car-like robots, while others are holonomic constraints such as robotic arm. To sample the nodes, algorithm uses uniform sampling, intelligent sampling, or direct sampling depending upon the application. RRT star have been used in online or offline mode depending upon the availability of environment information. If environment parameters are unknown or highly certain, then local planning is performed, also called as online planning, whereas a known environment requires global planning, also called offline planning or map-based planning. The paper also includes the limitations addressed by variants of RRT star in recent years and highlights the future challenges, out of which some are discussed here. RRT star requires large number of iterations and sample to avoid local minima, consequently increasing the memory requirements. During recent years, RRT star based planners have addressed these issues by exploiting the search space using different sampling strategies which are shown in figure. However, these solutions, especially guided exploration-based solutions, also require a balance of exploration and exploitation in the search space. Traditional uniform sampling decreases the probability of node from narrow passages. Very few approaches, such as informed RRT star or homotopy-aware RRT star, are reported to specifically address the problem of optimal path in narrow passages. However, the optimization and reliability in the narrow passages using real-world experiment requires investigation. To conclude the presentation, the traditional path planning methods are not feasible for non-holonomic, cluttered, and high-dimensional problems, while RRT star has proved its worth for dealing with such complex problems. This paper presents the review of major contributions in optimal path planning using RRT star and its variants in recent years. RRT star based approaches have mostly addressed the issue of suboptimal path, slow convergence, and high memory requirements. However, reliability in context of online planners and non-holonomic constraints are still open research issues. This ends the presentation. Thank you.